Welcome to this lecture series in real analysis. In this lecture, we'll learn about square roots and let us recall what we need. Principally, what we need is the Archimedean property of the reals, or it is almost the same as this fact that the infimum of the reciprocals of all the naturals is 0. Basically, we just need to know the least upper bound property of the reals. Okay. Here are some problems for practice. And now let us get started. So we will define what is a square root, fix a real number. We say that y, a real number y, is a square root of a if y square is equal to a. So that's our already known. This is the definition that we know from high school. We note that if we have a negative real a, then it does not have a square root in reals. Simply because the square of any real is non-negative, and hence we cannot have a square root of negative numbers. And just for the sake of an example, the square root of 16 are, the square roots of 16 are 4 and minus 4. Only 2 square roots and 4 and minus 4. Alright, so here is our key theorem that we want to prove. Every non-negative real has a unique non-negative square root. Right? This is something that we know from high school, but since we do not define real numbers in high school the way we do now, we in fact do not define real numbers in high school at all. So we need to give a formal proper proof of it, even though intuitively this might be clear. Alright, so fix a positive real. If we had a equals 0, then clearly this statement holds for it. So we will only restrict our attention to positive reals. And now define the set S of all those real numbers which are positive and whose squares are at least a. We want to show the existence of a square root, but we consider this set first, and it should be kind of intuitively clear that the infimum of this set is a square root of a. And that is the approach that we take. Alright. So first note that S is non-empty. So S is non-empty simply because large enough real numbers satisfy both these constraints, and S is bounded below. Namely, 0 is a lower bound. So these two things are there, and therefore if we take the infimum, we get a real number. So y is the infimum of S, and as we said, we claim that y is the square root of a. So this is what we will prove. So there are two cases. We'll assume on the contrary, suppose not. Then there are two cases. Case 1 is that y square is greater than a. This is case 1. So what happens in this case? For any natural number n, we have this computation. We have that, and therefore just basic algebra, we subtracted a from both sides. Now by using the Archimedean property, or that infimum of the reciprocals is 0, the reciprocals of naturals is 0, we have, for large enough n, we have y square minus a exceeds 2y by n, and y exceeds 1 by n. So I want to justify this a little bit. So by the assumption that y square is greater than a, this is a positive real. And hence, by the Archimedean property, if you like, n times this exceeds this given real, and hence we have that for some n, for some large enough n. So we have that. And similarly, since y square is greater than a, clearly y must be positive. And therefore, again, by the Archimedean property, there is a natural number n such that n times y exceeds 1, which gives us this. And you take the maximum of the two natural numbers. One natural number you get from here, one from here, and you take the maximum of the two. That works for both of these. So this is where we use the Archimedean property. Maybe I will write it down. So using the Archimedean property. Okay. So we have these two things, and therefore, for large enough n, we have this thing is strictly positive. Why is that? Because this dominates that thing for large enough n. So therefore, this is strictly positive. And this is also positive. And therefore, or thus, let us not repeat therefore 2 times. Thus, for large enough n, this guy lies in S. Why? Because it is a positive real whose square exceeds A. So this guy lies in S, but this is smaller than Y. This is a number strictly smaller than Y. And hence, this cannot lie in S because Y is the infimum of S. So we already knew that this does not lie in S simply because Y is the infimum of S. But we have concluded that it lies in S, and that is a contradiction. This is a contradiction. And this concludes case 1. Case 1 cannot happen. Similarly, case 2 is... Oops, I don't have a page. So case 2 is... that y square is less than a. Did I write a c somewhere? No. Y square is less than a. And similarly, I mean, the reasoning will show that. I'm not writing all the steps, so we will end up proving that for large enough n, we would have this thing less than a. Right? But since y is non-negative, the infimum of a subset of positive reals is definitely non-negative. So y is non-negative. So we have a positive real whose square is less than a. And therefore, this guy does not lie in S. And therefore, everything smaller than this does not lie in S. And therefore, the infimum of S will be exceeding this guy, will be at least this guy, which contradicts the fact that the infimum is Y. Right? So for large enough n, this will be the case, and then what will happen? So then I'm just writing down what I just said. So then this is a positive real, but this does not lie in S. Therefore, if x in S, then x is greater than this guy. Greater than, let me just say greater than this guy. So why is this? Because if something is not in S, everything smaller than it can also not be in S. That's the nature of S. Just think about that. So we would have that, and hence infimum of S would be at least this number. Again, here for large enough n. So this, once you fix a large n, only then we are talking. So infimum would be strictly greater than y, which contradicts the fact that the infimum is y. Right? So in either case, we would have a contradiction. And that finishes the proof of existence. We have established that there is a non-negative square root because this number is non-negative. We should have said this here itself. Y is non-negative. It is the infimum of a set of positive reals, and hence it is non-negative. So we have a non-negative square root for sure. And now for the uniqueness part, did I say existence here? I did not write it. Yeah, so this was the proof of existence. Now for the uniqueness, say we have two square roots, y1 and y2 be non-negative square roots of a real number a greater than 0. So then we have both these equations, which implies the difference of these two numbers is 0, which gives us this product is 0, which means either y1 is equal to y2, right? Now since a is positive, both of them are positive. They cannot be 0 because 0 square is 0. So this is a positive number and hence this is not a possibility. So this just means y1 is equal to y2. So the proof of uniqueness is trivial. Right, so we have proven that any positive real has a unique non-negative square root. And if a were 0, then clearly it has a unique non-negative square root, namely 0. So fine, I mean this proves our theorem that every non-negative real has a unique non-negative square root. And to conclude, we have this function. First define this set. This is all non-negative reals. And now this function, which is defined as, so it just squares what it is given. And the fact that we want to state is that the map F is a bijection. Why is it a bijection? Well, every non-negative real has a unique non-negative square root. That's it. That's the reason it is a bijection. So this is what we have already proven in the previous slide. Okay. And lastly, the graph of F. So the graph of F looks like this. For the input 1, it outputs 1, but otherwise it grows. So this graph, I'm sure we are familiar from high school. Right. So all we are so far doing is kind of putting things on a firm foundation. All of this is very important. And the proofs are very important. We need to get familiar with and comfortable with this style of reasoning that we just did. All right. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.